Hi everyone, thank you so much for joining the guest speaker session today at Prepare for AI. We have with us three guest speakers from Google DeepMind. Roopal Garg is a staff software engineer at Google DeepMind, where he works on improving multimodal content understanding. His focus is on building high-quality data sets efficiently and using them to develop autorators and metrics to advance and evaluate modern vision language models. Recently, he has been focused on hyper-detailed image descriptions, their implications for text-to-image models, and expanding these capabilities to include global geographical and cultural understanding. He received his MS in computer science with a focus on natural language processing from University of Southern California in 2013. Burcu Karagol Ayan is a software engineer at Google DeepMind working on multimodal datasets, specifically very detailed image descriptions that are culturally rich. Previously, she worked on responsible AI for text-to-image models and various natural language understanding problems. She is passionate about cultural impacts of technology and making technology useful for the society and world. She has a PhD in natural language processing from University of Maryland College Park. Andrea Burns is a software engineer at Google DeepMind working on vision and language problems. Her current work concerns fine-grained vision language understanding, improved metrics for vision language tasks, and how to learn from small amounts of high-quality data. Previously, she completed her PhD in computer science at Boston University with a focus in multimodal representation learning for digital domains such as web pages and mobile apps. She has continued interest in grounded and embodied multimodal understanding. Thank you so much for your time and for this session, and I'll pass it over to you.
Thank you very much for the introduction. Hi, everyone. As Emmett mentioned, this is Roopal, along with my colleagues Burcu and Andrea, and we would be presenting our paper ImageInWords, Unlocking Hyper-Detailed Descriptions. And okay, let's start. All right. Before we dive deep into the paper, let's take a short trip down memory lane and see how and why we got here. So when we talk about multimodal learning, the advent kind of started with having these having these supervised fine-tuning tasks on small-scale datasets which were curated for specific tasks such as captioning, VQA, retrieval. With time, we had the advent of pre-training into the mix, and that brought about this notion of having medium to large-scale models. We're now talking like millions to even billions of data points. And with it came the noise in the data sets. Now, this noise was noted even in the first wave of visual language pre-training on specifically tasks like captioning. So when you think about the first wave of data sets like conceptual captions, which was in the range of like around tens of millions, given that they were largely scraped from the web and had alt text as kind of their target, they were deemed as being basically too short and simple. In the second wave of the visual language models, when this scales increased from being tens of millions to now being hundreds of millions to even billions, it started being a bigger of problem, specifically for tasks like generation. And to some extent, this was deemed intentional, where you had papers like Align, which said we specifically trained from noisy text supervision, which helped them for tasks like alignment, but for tasks like generation and understanding, this was deemed a problem. So we kind of said that, okay, let's take a step back. Let's see where we are. And, there is this old adage of an image is worth 1,000 words. How do our best models do this? Now, take into account, this was mid last year. Gemini and models like GPT-4V were not readily available. So we were still working with Pali when we started this. And we realized that for an image as complex as this, what we had on offer was alt text like tasty yogurt, Pali models ranging from 5B to 55 billion scale, giving us a very, very high level notion of what things are. So we said, okay, this is fine given the kind of data sets we have. But if you actually look at the image, what if there were data sets that could give you something like this? And this is still not the best that we came out with, but this was kind of the early thoughts that, hey, there are tons of fruits here. There's a tray here, this, beautiful ceramic vertical two-stack tray here. Let's talk about the different kind of yogurts we have, different kind of fruits we have. How are they arranged? What is the light setup in the image? How is this image really taken? And what is it trying to portray? So we said, okay, how do we do this? So we started with this philosophical goal of, okay, let's have image descriptions that help you paint a vivid mental picture of an image in the mind of someone hearing the description with their eyes closed, such that when you open your eyes, the imagined image closely resembles the true image that you see in front of your eyes. Now, this is very philosophical. So we said, okay, easier said than done. How do we actually make this a reality? And what would be the use cases that come out of this? So we said that, okay, if you actually had these hyper detailed image descriptions, we could actually unlock a lot of downstream potential. This could help with image retrieval because now you have tons more metadata about an image. You could actually do better VQA because now you have more details to target and more details to actually answer VQA. This could help with editing because you have more stuff to about the image that you can actually edit. It could help with evaluation, alignment-based evaluations, and of course T2I, which is the big thing right now. So we introduced kind of our work called ImageInWords, aka IIW, where we wanted to basically go from images that you see on the right to the hyper detailed description that you see under it. Now, this is easier said than done. So we said, okay, to go from here to here, the first thing that we need is how do you even have humans compose this, right? So we contributed and created this first of its kind extensive guideline, which we have added to the paper for annotators to basically understand how to interpret images, how to note down details, and not just stitch them together, in random way, but how to actually compose image descriptions. We created this annotation framework, which is a seeded sequential framework, which we'll see in more details. And then we validate the usability and the viability of our data by fine-tuning downstream models on this and seeing the performance against the best there is to compare out there. Now, as part of the human annotation task, we'll basically be going through 3 steps. First is the guidelines, the framework, and then an analysis of the framework. It's why did we make these design choices and what came out of it, the data set itself. All right, let's go to the first step, which is the guidelines. Now, in the paper, there are about 5 to 6 pages of like detailed guidelines on this. Here, we'll do like a very high level thing on it, just to note the key points. Um, so one of the first things that we said that, okay, when someone tries to create these image descriptions, they should think of them as if they're instructing a painter to actually paint this image. The reason we said that is when you instruct someone to recreate something, right, you focus on the high level picture first, you focus on the key aspects first, and then you start slowly filling in the details in kind of a saliency respecting manner. And that naturally helps people create a frame of thought that helps them create these descriptions. One of the key things, kind of a new thing that we noted, was there should always be a TLDR to this image description. The reason we say that is it sets a very high level notion of, okay, what to expect from this image. And it also has a downstream use case because a lot of our VLMs and evaluation models actually can't ingest the whole length of the description that we have. So this TLDR acts like a very nice summary of the overall description. We kind of created this notion that you should err on the side of higher precision. Let's not try to hallucinate even in the human authored description. Let's stay away from that. And let's only note the details which can be verified using visual clues. And it should be written in a fluent, coherent manner. Avoid the use of filler phrases like, in this image we see, because it adds no value, just adds fluff text to it, and that's not useful. Among the things to focus on would be individual objects, relationships among them, the overall setting of the image, background, style, camera angle with which the image is taken. This is really important. We'll see in the next slide. The overall composition, and then we added some extra information on how to deal with text when there is text in the image, and how to deal with when you have people, places, and art pieces in the description, since these are very domain-specific tasks, so to say. Okay. Now, when we say why camera angles are important to note is if you look at all of these images, they all have kind of a precedent to them, right? If I say I have an eye level image, you already automatically have a notion that what kind of detail and what like representation you're going to have. When I say a worm's eye view, you already know, okay, you're going to be looking up, right? When I tell you it's a top-down image, you know you're going to be looking down. A Dutch tilt is kind of, tilted frame. So you already have, it creates a precedence of what kind of information to expect. Text was a big thing because usually what we saw in data sets was, XYZ text is written in the image. But we said, but okay, but if you say XYZ text is written in the image, it could be written in numerous ways. What font is it written in? How is it aligned? Is it stacked together or written in a single line? So as an example, if you check over here, juice across the universe, he said, just don't tell us that juice across the universe is written in the image. Tell us that juice across the and universe are three phrases which are stacked vertically in a slanted manner. And then focus on the details of each. Tell us how juice is written. Tell us how across the is written. Tell us the font and the manner in which the universe is written. And additionally, like for this free arcade game, tell us like everything is in uppercase. So tell us the casing, tell us the font, the color, the alignment, and details like that. That kind of helps us understand not just what is written, but how is it written. Okay. Now, next, let's go with the framework that we achieve this annotation in. So we break our annotation down into two high-level sequential seeded tasks. First one operates at kind of the object level, where in order to seed the annotation and to get object level fine-grained information, we first over an image run an object detection model. We get the regions of interest, the objects that there are. We seed the bytes within each of these frames to existing VLM and get like an object level caption. Now these tend to be noisy because some of these objects might be really small and they might be actually missing the context of the image, which at this level is okay. And then we have this feed to human annotators, whose job it is to refine them. At the end of this, what we get are object level detailed descriptions like these, where you can have a short-haired white and black cat sitting between the lamp and the spiral book on top of the table. So the humans can add a little bit more context in the description that was initially missing because the VLMs never saw the full image. As a next step, we say, okay, let's take all of these object level descriptions let's create the best image description that our VLMs can create, and then feed this metadata to humans and have them refine this sequentially to create that hyper detailed description that we want. And this then starts looking like this, where we have our object level annotations, the cat sitting on a table next to a lamp being the best VLM descriptions that Poly could create at the moment. And then humans kind of refining, building on top of this in multiple steps to create this 200-word description at the end. The good thing about this is since this is done sequentially, there is always kind of a guarantee that the next thing that you get is going to be better than the previous thing because they're strictly kind of building on top. All right. And then I'll hand it over to Burcu to discuss the framework and the dataset analysis.
Hi. Okay, so now that we have seen what our annotation framework looks like, let's dial in and see what kind of analysis we have done for the framework. Next. Roopal mentioned that we are doing sequential annotation. So this was a very design choice that we chose, and we want to give you the reason for that. So we believe this gives an advantage over parallel annotation, where multiple annotators are writing descriptions on the same image separately. We counted the token numbers for each annotation round, and as you can see here, the next please. The token counts are going up, which means we are getting longer annotations, whereas the time each annotator spends on an annotation round is going down with the sequential annotation. Next. When we have 3 annotators writing descriptions for the same image in parallel, we would have 3 competing image descriptions per image. And this is not really good because each will have its own style, each perspective, and each comes with its own pros and cons. Also, when we have these parallel annotations, each will have around like 170 token per description, and it takes around like 700 seconds. This is 13 minutes. That's a very long time. Next. When we have done the sequential annotations on the other end, at the end, we are getting this one single all-inclusive output image, and it is verified by all and augmented by all the three human. So they are just adding more information, more detail, making the description richer. On top of that, overall token count is increasing, and each annotator is spending less time as time goes by. Next. We also check the Jaccard similarity between these rounds. So when we check the early annotation rounds, as you can see, there's a very low Jaccard similarity between round 1 and round 3. This is like the first and the third annotation. And as time goes by, the second and third annotators, the Jaccard similarity is increasing, which means they are writing, similar things. Next. However, we also had a really interesting observation here. As time goes by, if we are using a constant annotator pool, which we have done, there's an implicit feedback loop. And at the later annotation rounds, the Jaccard similarity between the first and second annotator also becomes really high. So we haven't observed this before, but at the end, the second and third annotator with the earlier rounds are same as or very similar to the first and second annotation rounds in the later ones. So which means that this reduces our human variance and biases. Next. So this is what we mean by like human in the loop implicit effect. This constant annotation pool, each annotator sees what the other annotators are writing, how they are writing, their style, their perspectives, what they are giving information about, and they learn from each other. And as a result, the quality of each annotator is also improving. Next. Now that we have seen the framework for our annotations, let's see a little bit of statistics about the dataset that we achieved at the end of this using this framework. So we are comparing our ImageInWords dataset with the prior datasets. And in our experiments, we are specifically using DCI, densely captioned images, and dossier, descriptions of connected and contrasted images. So DCI is a mix of human and machine outputs. Unfortunately, it doesn't allow like updated machine outputs. Dossier, on the other hand, utilizes only human annotations, so we don't have any machine outputs in that, but still it is much less rich than ImageInWords datasets. Here, if you look at these numbers, overall, ImageInWords datasets have more tokens per sentence, more tokens, sentences, and different part of speeches per description. And some of these are quite, a jump from the next previous richer dataset. Next. Okay, so in ImageInWords, we have both human-authored and machine-generated data. But how are we evaluating the quality of these descriptions? That's a very good question. Let's talk about this. Next. So we use both automated metrics and human side-by-sides evaluating our collected data. The overall advantage of the automated metrics is they are fast, you can reproduce them easily, and we don't need any human annotators. We look into captioning metrics and readability metrics that was introduced before. Unfortunately, the captioning metrics are not really suitable with this kind of long descriptions, and they really show poor correlation with the human judgment. As for the readability metric, the aim is to capture kind of like what kind of grade level is needed to understand this text, but they are not very holistic metrics. If you want to learn more about these metrics that we use, please check out the paper. For the time of sake, I'm not going into the results here. because we believe the human side-by-side metrics that we introduce are giving a better understanding of our image descriptions. So the advantage of human side-by-side is you can get really high-quality human judgments on these descriptions. The disadvantage is, of course, they are really costly with respect to both time and budget. For our purposes, we introduced 5 different custom metrics, and we use a 5-point Likert scale, which means that we are asking our annotators or raters to compare 2 descriptions and asking them, are they marginally better, substantially better, neutral, marginally worse, or substantially worse? So we believe breaking down into this like 5 metrics instead of just saying one is better than other or gives us a better understanding of these descriptions. Next. So I mentioned that we introduced 5 evaluation metrics for the human side-by-sides. These are comprehensiveness, and here our aim is to measure whether the descriptions capture all the important elements in the image. The next one is specificity, and here our aim is to measure whether these descriptions are using precise descriptive language. We don't want these vague or ambiguous descriptions. For instance, instead of saying there's a cat and dog sitting next to a river, we would like the descriptions to actually name these cat and dog breeds, like, hey, it's a Labradoodle and a Scottish fold sitting by the river. Hallucinations is always a very big problem. So we want to also measure that the descriptions are factually correct. They are not making any assumptions or interpretations. Everything is supported by the visual cues that present in the image. We are also looking into what we call first few lines as TLDR. Here our aim is to see if the image descriptions, the first few lines of the image descriptions, are painting a high-level picture of what to expect from this image. It's kind of like a summary of the image. We believe this is really important for especially these detailed, long, rich descriptions, because it sets a precedence, what to expect from the rest of the image description. It creates an overall picture before getting into the details. And lastly, we want to see if these image descriptions sound like they are written by a human. We don't want it to see that, hey, this is machine generated. So it should be free of such artifacts. In fact, it should be written by a kind of educated person. Next. So this is a snapshot of the annotation UI we are using for the human side-by-side. As you can see, the annotators see the image and 2 descriptions of this image, and they are asked to choose this 5-point scale for each 5 metric. And also we are giving them an option to explain why they are making these choices. This really gives us an idea of what's good, what's not good in these descriptions. Next. So when we use this side-by-side to check the quality of our human-authored dataset part, here are the results. So we are comparing with both the DCI and DOSI test set. And you can see here, the 2+ signs, 1+, and the neutral minus. Here we are reporting the percentages comparing data. And in all these fields, IIW is performing much better than the others. And in some cases, the numbers are, we are very proud of these numbers. Next. Now I'll hand it to Andrea, who will talk about the model evals and our experiments.
Thanks, Burcu. Yeah, so now we'll talk about the results we find when actually fine-tuning with our ImageInWords data. So let's get into it if you want to go next. So similarly, with our generated outputs from fine-tuning with ImageInWords data, we can also use automatic metrics like classic captioning tools or readability metrics, as well as our human side-by-side that we've developed for evaluating these generated descriptions. So similar to the human authored results, we'll kind of skip over the automatic metrics, and please take a look at the full paper, or if we have time, we can discuss that a bit after in the question portion. And in addition to the human side-by-side results that I'll go over now, we also look downstream to task evaluations or kind of applications that we could consider as a proxy for better evaluation tools in place of having, poor current captioning metrics that don't really suit our long, hyper-detailed image descriptions that we're now working with. And the two tasks of interest that we'll study are image description. So we ask this question of how faithful are images that are reconstructed or generated with our ImageInWords model descriptions, and also look at vision language compositionality. So that's kind of been an existing issue in prior work or current state of the art for VLMs. And we ask, can we actually use our model generated descriptions to better distinguish between true and false image text pairs? And so this is really great to also see how can our fine-tuned models be used to aid in other tasks that are of interest in vision language areas. Next. So starting again with the human side-by-side evaluation, we're now comparing our fine-tuned ImageInWords model to those fine-tuned with DCI or Dochi, and we also compare to GPT-4V for a more recent comparison. And you can see, again, very similar to the human author data, we make really large gains still with our fine-tuned model versus DCI and Dochi models. So comprehensiveness, specificity, TLDR, and human likeness all still have really large gains, which is awesome to see, with some marginal trade-offs on hallucination. And we note that this is to some extent expected, given that, again, we have such longer, more rich and specific descriptions, that with this style shift, there's a little bit more room for hallucinations potentially. Then when we look at the GPT-4V comparisons, we still make also really big gains when we're comparing the human author data. So if you look on the right-hand side of the table in red, we're comparing GPT-4V model outputs to ImageInWords human author data, which is a bit different from the left-hand side of the table. And so we're still seeing, 35% improvement in comprehensiveness. Human likeness is boosted by 70%. So again, there's still such higher quality in our human authored curated data, which is really important to see and shows this gap in quality. It is a bit less competitive or more comparable to GPT-4V on the model-to-model comparison, but this goes to show that we might just need a larger parameter model to really be boosting performance to that extent when fine-tuning, given that, again, we're working with Poly 5B fine-tuning, which is by no means an apples-to-apples comparison with our model setup. Next. So moving on to the task evaluation portion and starting with the text-to-image reconstruction, again, this question that we're asking and want to evaluate is, do ImageInWords generated descriptions produce more controlled and more specific images? And so the first step in our task methodology or experiment setup is to actually generate descriptions on images using our fine-tuned models. So we take images, these original images are a subset of localized narratives, and we pass them through our fine-tuned models. So they're either, fine-tuned with ImageInWords, fine-tuned with DCI or Dochi. And then we generate these image descriptions from each respective model. Next. In step 2, we then can generate images using a text-to-image generation model, given those generated image descriptions. So you can see in green, we're taking those generated descriptions from model A or B or C from each respective data set that we fine-tuned with, passing it through a T2I model, and then generating images which we consider reconstructed images from each respective description. Next. Another thing to note is that in addition to passing through the entire generated image description, we also break it up into sentence chunks where we kind of ablate how much the text-to-image model is seeing of each description. So we pass in just the first sentence, then the first 2 sentences, and then the first 3 sentences, and so on. And this gives us a sense of how much each sentence is actually adding to the descriptiveness or richness in the description, which is important because we want to make sure that the gains we're seeing are not just about the length of our descriptions, but that we actually have much more part of speech richness and much more specificity and so on. So that's a useful tool to see to kind of de-bias from length and also see what actually gets added as we add more detail with each sentence. Next. And so then in the final step, once we have the original image that we started with from localized narrative and all of these reconstructed variants from each generated description, we can compare these two images to see kind of the quality that we can obtain from our fine-tuned models. And we look at both a human evaluation, so that's a three-way human ranking evaluation, as well as using clip similarity between these two images as an automated metric. Next. So looking at these results, what you want to see is low mean rank, which means that you were ranked higher, kind of like higher quality would be ranked first. And then clip similarity, you want to see higher similarity scores. And you can see across the board, the ImageInWords fine-tuned models result in higher human evals and higher automated metrics like clip similarity. So this is really awesome to see. It's also important to note that this is consistent, again, across those sentence chunks that we broke our descriptions into. So it's not just, oh, when we have the full description, maybe we add a couple more details, but at every sentence that we add, we're still being ranked first more often or having the highest clip similarity. So again, this is about the richness and the hyper detailed aspect of our description that's really novel and reaching state of the art. Next. So now we have some qualitative examples, the first showing when we just input that first sentence from each, respective generated image description. So generated from the fine-tuned DCI model, the fine-tuned Dochi model, the fine-tuned IAW model. And you can see immediately the similarity from the original image and this reconstructed image provided by this ImageInWords description. We have, again, this camera angle is spot on, which we've noted has been really important in our guidelines. We also see details like the pasta shape is really accurate. And so it's really clear to see that even at that first sentence, we're able to reconstruct much more higher fidelity images. Next. We also have this qualitative example for this image that's like a globe or lantern style light. And you can see if you go from the first row moving down to the bottom, starting from just inputting the first sentence to all of the sentences from those generated image descriptions, that ImageInWords is able to incrementally get much, much closer to this original image, right? So we're incrementally able to add details. And that shows that each sentence is adding more richness and actually useful information. It's not just redundant length being added, but that actually each sentence is useful to this task. So that's really great to see. And also overall, it just gets to be the closest reconstruction. Next. So for the second task that we look at, again, we studied vision language compositional reasoning. So prior work in this space has proposed probing data sets that have shown, current VLMs are often noun and object centric. And as a result of that, they're often insensitive to verbs and other parts of speech that are important for multimodal understanding. Also, it's been shown that these models can be bag of words models where they're insensitive to word order, which is an issue for relational understanding. And so we use these types of data sets to pose the question, can we generate, descriptions that have finer grained details and better coverage over all parts of speech and all types of objects and relationships in the image to better reason about image text pairs. Two of the data sets in our experiments are illustrated here. So on the left, we have the arrow data set with a visual genome relation example shown. So for this image of the horse, there's always going to be a positive and a negative text pair. So the positive is the horse is eating the grass, and the negative is the grass is eating the horse, right? So these objects relations have been swapped to create that negative pair. Then for the Winoground data set, that looked at shuffling text to contain the same words for captions, but have different semantic meaning. So on the left-hand side, the matching caption A states some plants surrounding a light bulb. And then for image B, the negative would be that caption that states a light bulb surrounding some plants. So these kind of serve as the negatives for each other in the data set. And you can see that they consist of the same words, but have a different meaning. Next. So for our task setup in this case, it starts similarly with generating descriptions on images using our fine-tuned models. And so in this case, we're using these probing images from Arrow, Winoground, and then a third data set, SVO-Probes. And then we generate these descriptions over those images. Next. For step 2, we now set up this problem by predicting what is the true matching caption for the image in a text-only setting. So instead of passing in an image and looking at its similarity to both the negative caption and the positive caption, we actually replace the image with our generated image description. And we feed that in with kind of, a multiple choice question between the caption options and ask which actually matches this image description. So we pass this through to an LLM, in our case Palm 2, and have it predict what actually matches the image description. And then we can compute accuracy over that. Next. So looking at our results, we compare our ImageInWords model to prior works like Lava and InstructBlip. We also have an important bias baseline, which is this first row here, where, Roopal, could you actually go back for one slide for a second? So instead of actually passing in this green image description here, we don't pass in any for this bias baseline to kind of get a sense of how good are these data sets and how close to random are they. We'd like to get a sense of, can we actually decide what's the positive caption just from the linguistic phenomenon alone, to make sure that we can properly categorize our performance boosts. So next again. Thanks. So that's what our language bias baseline is. And again, we report on Arrow, SVO-Probes, and Winoground, and we can see significant improvements once we incorporate an image description. And in particular, ImageInWords is doing the best across these data sets. So on Arrow, we get as much as 6 absolute % improvement over Lava on the attribute subset, 2% boosts on the relation subset, and then on Winoground, we also see about 4% or slightly over 4% improvements. And again, that's absolute % improvement on accuracy, so it'd be higher probably for the relative computation. And so this is what we want to see, right? This means that our descriptions are capturing more of the objects, more of the attributes and relationship information between them to be able to actually distinguish between a positive caption and a hard negative that's often present in these probing data sets. For SVO-Probes, we perform quite similarly to InstructBlip within like about a point on accuracy. Next. Finally, we'll go over the data release that we share in open source and also have some concluding thoughts before taking questions. Next. So we open source what we call the IIW eval benchmark, and that consists of both ImageInWords 400 samples, as well as re-annotated DCI and Dochi images for fair apples to apples comparison. So those have been re-annotated with our full framework. We also enrich localized narratives and cross-modal 3600 samples. So we ultimately open source a mixture of human author data from our framework, as well as outputs that were generated from our fine-tuned model. So we hope that that can be useful to the community for looking at both, really rich and high quality human authored data, but also looking at, potential errors or room for improvement in our model generated outputs. And of course, this is enriching existing data sets that had much less rich image captions or, shorter image descriptions. And we also have stats on that in the appendix of the paper. Lastly, we include side-by-side annotations, so that also can be useful for exact reproducibility in future work and trying to kind of standardize our 5 metric side-by-side comparison. And as you can see in the columns of the table, we also share both object-level task 1 annotations from our framework, as well as the final image descriptions. And there's the links or QR codes for both Hugging Face and GitHub here. And we also have a link to the project page on the final slide. Next. So in conclusion, with ImageInWords, we were able to reach this new state-of-the-art dataset quality where we have over 217 tokens on average per description. And as we saw, significantly richer part of speech distribution with, more nouns, more verbs, adverbs, and adjectives. And a lot of this is coming from our framework, which was both seeded and sequential, trying to balance both efficiency and quality while having humans in the loop. And we also have this active learning element where we could update our seed quality over time and during our annotation process. We introduced this new human side-by-side eval suite, which consists of these 5 metrics like comprehensiveness, specificity, hallucinations, TLDR quality, and human likeness. And across both the human annotated human side-by-sides as well as the model-generated evals, we see that IIW consistently outperforms prior work. And then we looked at these 2 downstream tasks or applications of interest like text-to-image reconstruction, where we saw that ImageInWords these models were able to generate more controlled and more specific images, both being ranked first more often by humans, but also having higher clip similarities to these original images. And then for the vision language reasoning data sets, we see that our descriptions ultimately included more attributes, relationships, and objects to be able to boost accuracy on these probing data sets by up to about 6%, which is really awesome for improved vision language understanding. Next. So that's it for our talk. Thank you all for listening. And we also want to thank the rest of our team that worked on this project with us. We couldn't have done it without them. Again, here we have the QR code for the project page. It's also linked on the slide, and feel free to reach out at this email if you have any questions or want to follow up. And we're happy to take questions now too.
Thank you so much for the talk. I have a question. So currently, the data set that you have created, is it only in English language, or are there multilingual examples in it as well?
Currently, this is Ayan only. There is ongoing work to expand this, and yeah, we'll probably hear about it in good time.
Great. Also, another question might be a bit different, but in the beginning you said that it is different from captioning. Like how would you differentiate between a caption and a description? Like, can we call this a very detailed caption, or like
Would
does
you-
caption has a specific properties?
Burcu, do you want to take that?
So captions give a kind of like maybe overall feeling, and they are usually short. When we are saying descriptions, what we mean is these explain the images in very rich details, going over all the salient objects, their relations. In the traditional sense of captions, this is not what captions have. That's why we want to use not captions, but descriptions. So descriptions give a representation of the image. And it's also, the other piece is descriptions are really neutral and objective, whereas in the captions, and especially like the alt text usually used on the web, it's really subjective. It's meant to be more sensational. And then it's not really about what's in the image, but how you want to present that image. That objective language is really important to get out of the emotion, and only grant the description on the visual cues in the image.
All right. I have another question. So, do you think that the order of caption affects some of the tasks that you evaluated? Also, for example, in an image, there is some primary object or some primary action, and then there are some background things. But if the description has the background thing first and then the primary thing, so would that or some ordering of these things would affect the downstream tasks?
Yes, I think in the paper as well, we note that in the guidelines, there is this notion of that it should be composed in a saliency respecting manner. The reason we say this is both from a practical point of view and from a proper flow of the story point of view, kind of thing. From a practical point of view, think of a scenario where you have, an image depicting a coffee shop where you have two people in the foreground talking, the actual, focus of the image, and you have five people behind them kind of blurred out with less detail. Now you would want to focus on what the image really wants to focus on first, and the background can come as a TLDR, and then later in the description you go into the detail. From a practical point of view, this has implications because not all the models can actually ingest this whole big 200 plus word description, they're going to trim it off at some point. The place that this gets trimmed off, you would want the most important focal point information to actually pass through, and then maybe some of the background details and less important details to get trimmed off. Whereas if this is jumbled off in a random order, you really don't know what goes in, what goes out. Right? For the other is for models, it's better if you have a coherent story rather than sentences, jumbling up things. If you have details about an object X, you would want all of it together rather than, some of it mentioned at the beginning and some of it mentioned at the end. Because then it becomes a tougher task for the models to connect the two, saying, hey, these two details are actually about the same object, not two different objects which are similar.
And also, I want to add, I think as human beings, this is how we interpret an image. When you first see an image or a photo or an art piece, you first get a overall feeling, and this is both like camera angle and also the TLDR in our case. Also, then you start to pay attention to more salient object, and sometimes it's like a cat and dog, they are more important equally, and then it doesn't matter which one is mentioned earlier. But then as you look more and more to the image, you start to realize the details, the background, the smaller objects. And this is what we want in the descriptions. So it is following as humans what we are understanding from an image.
Got it.
Yeah, go
You
ahead.
can unmute and ask.
Yeah, thanks. There is this FLD5B dataset from which was proposed in Florence 2 paper, where they have formulated the problem statement in such a way that the image descriptions are given along with the segmentation mask, the object detection bounding boxes, etc., along with a few other multitask prompts. They suggested that this kind of dataset helped them to create a single model which can handle many tasks out of it. Does the IIW dataset have annotations in a similar manner, or do you guys plan to do that if you have any insights there?
Yes, I think so. The annotations are done in a similar manner. Instead of segmentation marks, we have objects because we wanted to do kind of an object detection, but I don't see a difference, like a marked difference in the output. When we actually fine-tune the model in the appendix, actually there is single poly 5B model that we additionally trained, which combined task 1 annotation and task 2 annotation. We actually created 7 training tasks out of these 2 data sets and then created a combined single model that could do all 7 of them. It's there in the appendix. So yes, in theory, it's kind of the same thing, I guess. You could do all of them together. It would depend on you actually see a boost or not. For our case, in particular, image description was the primary task, and we did not see a marked boost on it. So that's why we did not promote it too much in the paper. But all the details and stats are there in the appendix section. Does that answer your question? Just to check that.
Yeah, thanks a lot.
I have a question. So actually, I wanted to ask if this framework can be extended for document images or images containing rich text, because the current vision language models, uh, there is really large scope for hallucinations there. And if we take human in the loop, it would take human like a very long time to get the full image. So, is it applicable?
I think definitely you could boost it from whatever the best VLMs that are available and have the VLM do kind of the heavy lifting. You could also inject like OCR as kind of a metadata, giving to humans saying, hey, this is the OCR text that we have extracted. And then humans kind of can come in and kind of fix the OCR and the VLM detection, stitch it in a more organized manner, saying, this is the first line, this is the second line. Focus more on that. So I think definitely it could be extended to documents. It might actually go faster because there the annotation task is more objective compared to images, which are slightly more subjective and open to interpretation. So it might actually be easier. Does that answer your question?
Yes, yes, thank you.
I have another question. So generally, text to image models, especially like the early versions of Stable Diffusion, 1.45, they are not good at the object relationships. And you have like in the images, in the data set, you have mentioned about the relationship, the spatial relationship between the objects. So have you done any study on does it improve these spatial relationships in generating images?
Not in particular with respect to T2I specifically. We did try it with the being able to distinguish in terms of like pure LLM-based relationships, some of the experiments that Andrea mentioned, but not explicitly for T2I. This might be a downstream experiment that we do on whether this helps T2I relationship representation or not. We think it would, because if you pre-train on this kind of data, then you have a better chance of being able to learn these relationships at a more ground level.
Right.
So, but this is TBD in terms of actually getting the numbers out.
One more question is, so you mentioned about the look. I do not exactly remember, but in the earlier slides you mentioned about in the annotations you mentioned about like having specific person or artist or description. So does in that data set, so for example, if a celebrity or any kind of specific location appears, so do you like so what's the policy in that case? So do you like censor it, or is it like specifically tagged by the name of that person or location?
So for the annotation, we let the annotators use Google image search. So they can right click on images and kind of try to deduce like what the location or the person is in particular. If it gets into like PII territory, then we kind of filter out the image entirely. We don't include it in the data set. But if they're more like renowned celebrities, then and the data set is openly available already, then we include it. But yes, the annotators are free to use Google image search. Thank you, Amit, for giving us this opportunity, and hope this was helpful to everyone.
Thank you so much for your time. It was really an insightful session.
Thank you, everyone.